This is lecture number 28. And let's recall the LSC reduction formula. The point of this formula was to relate what we want to know, the inner products of these asymptotic states, in states, and out states to expectation values of fields, because we believe that with the field you can actually compute something. We haven't got there, but we turn them into fields. And the idea is you will compute the time-ordered vacuum expectation value of a bunch of fields, and you have to take as many fields as you have particles in the in plus the out state, and then you go to x1, and that phi n. Right, and before you transform this thing, in all the variables, e to the minus I, di, xi, b 4, xi, I from 1 to n, integral. And that's called the Fourier transformed time-ordered endpoint correlation function. It's a function of the moment of P1 to Pn. And here, for simplicity, everything is the same kind of P inside here. And so here we have in and out, so we distinguish. What goes there is the G with the incoming momenta, P1, P2, and so on. And then the negative of the outgoing, P1, K1 minus K2, and so on. This turn it around, there's a different sign for in and out. It doesn't matter where they go. You can start with the K's, with the minus K's, and the P's there, or in any order, because this all commutes, and here the order doesn't matter because time ordering will take care of it. So anything is fine. And once you have computed this, you pick out the singularities, the coefficients of the singular parts. So there will be infinities in this, and we multiply by zeros. So minus kj squared plus m squared for all the outgoing ones. So this goes up to a L, say, and this to n, and then all the incoming pi squared minus m squared product and I is m1 to n, and then there's a factor of I for every leg, and that's that. Today we'll continue working on this, and we'll also see very soon these divergences, and I'll be able to make a comment. That's the formula so far. We have started with the free 2-point functions for 3 2-point functions. Really, we care for the time ordered. Time through. The correlation functions if you have the space. And we'll spend most of the time today, if not all, on these 2-point functions. My secret hope is that I'll be able to go to the Wick theorem and we have all the endpoint correlation functions, but you know, we always go a little slower than I hope. I also want to be understood. We've made 2 definitions. D of x and y is this expectation value. And here, C, we're talking about C. So there's this normal vacuum, everything is easy. These have the normal mode expansion that we had, and everything's good. We're just learning. Next week, that's for sure not today. Next week we'll relate the one here for the interacting theory to this. This won't be in vain. There's another formula which connects the two, but it's also big formula. So let's learn how to compute these things, the time order, two-point functions in the free theory first. So that's the definition without the time ordering, and with the time ordering, with the dx. D I x I y. And this is the interpretation of the probability amplitude to propagate from the first argument from y to x. And this is the interpretation for the amplitude to propagate from the earlier of the two to the later of the two. And we can expand it out by using the definition of it. So it's theta x0 minus y0 if this argument is positive, so x is later than y, then it needs to go to the left, later to the left. So it's the one with the x to the left, so we can use this notation. It's e x minus y, or theta y0 minus x0, the other order, and then it's the other order. So that's a relation. And we had an expression earlier from this plugging in the mode extension and using the commutation relation for the integration relation operator as this thing, d3 t cubed 1 over square root 2 e to the minus ip times x minus y. And now, using this here, we would in principle have also an integral representation for a Feynman propagator, which is really what we're after. But it's not pretty at all. It has these theta functions in there. It's just a 3-dimensional integral. I really want the 4-dimensional integral. And you could fudge it, right? I mean, there is a nice expression. And one way of writing is just to force it and then guess, and some books do that. They just manipulate this expression. But a different way of getting to this representation of the Feynman propagator in terms of a 4-dimensional momentum integral is to look at the differential equation. So that's also what we did yesterday. We prepared it. We saw that the normal, the D, satisfies the homogeneous time coordinate equation with a 0 here, while with the F, the time derivatives that are here hit the time ordering symbol, basically. These two functions, it produces some extra stuff, and with the canonical commutation relations, we figure out what they were, and they were just delta functions. With a minus I. So that's really a 4-dimensional delta function. The 2-dimensional, the 1-dimensional, the time came from here, derivative here, and the rest, the spatial part from the commutation relation. So that looks pretty. And so now we can use this equation to find an expression for df by going first to Fourier. I mean, I really want the Fourier representation. Why? Because this is all Fourier bits, right? So, how does this work? We define df of x minus y as the 4-dimensional Fourier integral. 4, and then you have dx tilde of p e to the minus I p times x minus y. That's now a definition of this. And it picks the sign that we want. You can have different normalizations, of course, you can do different signs. This is how I want it. And there we go. Here's it. If I insert it here, the derivative x there really brings down a minus ip to the squared of a minus b squared plus x squared on I'll define this df p, all under the integral sign, and on the right hand side we have this delta function, but the delta function we can also write as a the delta x minus y is a similar integral before e to the 5 over 4 with 1 here, e to the plus or minus the 11. This. And so after da da da, it is equal to minus I. Let me know if I should do this somewhere more explicitly. We've done these Fourier transformations before, so I think you'll let me know, right? It makes sense. This turns into this. And beautiful. Now let's solve it. Now algebraic. We can just divide through and absorb a minus sign. Looks like this. There it is. This is the Fourier transform of the final propagator as a solution to this equation, to this Green's equation. And if I insert it back here, I have this. Let's do it. Let's do it here. df x minus y is equal to integral b4p pi to the 4 I divided by p squared minus m squared e to the minus ip times x minus y. Beautiful. It's just beautiful. Now look, this is the D is this three-dimensional one with this stuff in there. You have two of the D's. You put these theta functions together in the sum, and the result is that. Pretty, huh? But there's still at least 45 minutes to talk about. Before we talk about this 45 minutes long, we will appreciate this denominator. How big is that denominator? Like p squared minus m squared. Right, so if the p is an on-shell momentum, the p squared is m squared. So we have exactly the pole, right? So this is a 2-point function. It's a 2-point time-ordered 2-point correlation function. And we see that its Fourier transform has this pole. See? No magic, this just happened. So it is conceivable that these higher order time-ordered correlation functions have poles in their Fourier transform. Exactly the poles in these on-shell poles. And so with this formula, LZ, you take these poles away and just keep the numerator, the coefficient. I just wanted to give it, here was very abstract. You say, oh yeah, this is divergent, and then with these zeros, 0 times infinity, gives you something, and here you see an example. The example isn't absolutely perfect. First of all, here, you're supposed to Fourier transform in all the coordinates in x, 1, 2, 3, 4. So if I have a 2-point function, I should have 2 Fourier integrals, x1, x2. Here I've written only 1, really. I treated the difference basically as one variable. So in fact, I should have the second Fourier transform of this thing. But it doesn't even depend on anything, right? So if I Fourier transform this the second time, I would just get an extra delta function. So let's see if the inverse u tilde p is integral of this df of x minus y. Here go the d4. Let's forget about the factors. I'm inverting this now. E to the I p x minus y. It's really what I did. If I do the right thing with two x integrations, I should think of it as x plus I q y d for y, and then I have a Fourier transform which depends on two things rather than one thing. What I did made sense in this context, but if I want to relate it to here, I should Fourier transform my two-point correlation function in both arguments separately. The first one will give me what I have here, and the second one will just, I mean, my whiteboard thing is looking bad already. I'll copy the EF tilde P here, place it here, and then say what it was if I had two arguments. I would have what I had with one, and the extra delta function. So, since I wanted to do it related, I have to relate it properly. Whatever that 2-point time ordered correlation function in coordinate space is, and if Fourier transform it, this is the G, this thing. It has two arguments, and that's how it looks with this extra delta function. Now we see it doesn't have two poles. You should here you're instructed for both legs. So you have 0 times infinity times delta function, and that's 0. I'm not getting anything out of this for my scattering amplitude. And that's okay because I excluded the case. I excluded the case where any of the p's is equal to any of the k's. But in this case, there's just two. They're going to be equal. There were many thoughts. Let's see what I've said. I'm computing just because I want this expression of this Feynman propagator, and I wanted the momentum space. And I'll continue there. But then I realized, wait a minute, it's worth making a comment about the form. Because the form has a pole. And aha, I remember pole was yesterday. These things are supposed to have pole. And then with these extra factors, you extract the residue, the coefficient of the pole. Fine. So do we have an example? Yes, kind of, but not really. Because here, in deriving this formula, I have only done one Fourier transform for the combined argument. And if I took this seriously, if I really wanted to do it in this context, I had to have two. And then the answer is not anything but 0. There is no scattering amplitude from 1 to 1 in that sense, in this formula, because in that formula, I didn't want any particles to just go through. Oh, okay, let's say, who have I not confused yet? Perfect. I've confused everybody. Zoom? Are you here? Can you
Yes.
hear us? Oh, yes, you can hear us. Are you confused?
Kind of.
Welcome. Let's continue, I guess. Forget the remark, essentially. I needed to know what you're confused about. That's the problem with the remarks. If I make a remark about an observation before you had the observation yourself, you don't know what I'm talking about, right? It was too early, my remark. You're thinking, I can see that.
Yeah, my question is, right now, with the free propagator, we don't really care whether the x's are the Fourier transform of the k or the p. So if we want to exclude the terms where the k equals the p, and because we get those delta functions we don't care about in the end, Wouldn't we also have to exclude the terms where the k equals the k's? Because so far the
Yes.
term
Yes,
below
yes,
does not care about it. So we cannot just send in two particles with the same momentum.
Yeah, I think, we gotta be careful, yeah. I'm, yeah, I think for safety, I'll just exclude them because they're special cases, but I don't think they're anything you can, there's a way to treat this too. You know, if you have two of the same, you don't have to have a different normalization, and you can write more complicated formulas. But we might as well just disregard them for simplicity now. All I'm trying to say is there's no fundamental problem with, or maybe there is, if two have the same momentum. Yeah, you don't even know, is it one particle with double the mass or is it two? And you might have difficulty separating them as external states. And I don't know. I think I just want to avoid these complications. Okay, let's go back on track. I wanted to find an expression for this guy as a four-dimensional Fourier integral, because that's convenient for later to have this in momentum space. It's simpler. If you gave it to me in coordinate space, I happily took it too, but it's complicated. And this is too abstract. So that's why we're working on this expression. On the way there, I saw this pole and felt the need for a remark. Forget that part and just let's go on with computation. Now we have this. There's four integrations, and there's this denominator, and the denominator is in terms of these four, it's p0 squared minus p vector squared minus m squared. And that denominator can be zero because you have pluses and minus signs. And if the denominator is zero, well, that's bad for the integration, right? How bad is it? Like say we are integrating over p0, then we have a pole of second order. So this, well actually no, this is separate. So this can be, this can be different. It's like the third binomial formula. So it's p0 minus or plus p vector squared plus m squared, or p0 minus p squared plus m squared. Does that make sense? So if I multiply it out, I get the p0 squared, and then minus square of the square root, so exactly this. And that's, it also looks nice in p. So it's not a second order pole, it's two first order poles. So if I draw my real axis, my function, it's pretty hard to draw this function. It's IN complex. So let's forget about it to draw the function, just indicate here 0, p0 is 0, and then p0 is minus EP, here is the pole. And since it's dangerous, I red here. Here's minus EP, and here it's EP. And so if I started to integrate over P0, the real line, the full four-dimensional Minkowski space, so P0 goes over the real line, and then I'll hit those poles, and this is divergent. And this is integral d P0 over P0 plus or minus. And that's log And then, yeah. You have to split the integration there because it's a pole, and then you can do the principal value if you wanted. But without saying anything, it's divergent. Okay, so beautiful. We have found something nice, but it looks simpler than it is. It's really divergent. And then there to make this well defined, we have to say what we do here. Like principal value would be 1, but we can also just go around it in the sense of the complex plane. So let's use this picture and say this is the real part of P0, and that's not the function, but this is the imaginary part of P0, and the function is on top of here. And then we integrate along the real axis shortly before the pole we stop, then we go around it, and then we go this way, and around it, and this way. So this is a way to integrate. This is a definition. This could be a definition. It's at best it's a definition. It's not. You see this and you say, okay, fine. Then that's the value of the integral. The value is not defined. It's nothing. But we can give it a value by saying, oh, the integration contour for P0 is this. But that's just one that I picked. You could have different choices. And one would be to just go around it below. Or, this is really funny, below, above. Or just because we can, this. So now we have come up with 4 different ways of defining this integral. And none is better than the other. And nothing is more natural than the other. And now we have 4 different values for the same thing. Which one is the right value? There's no right value because it's the solution to this differential equation. And the differential equation just has many solutions. And the difference between 2 solutions to this inhomogeneous equation is one solution of the associated homogeneous equation, right? We can try this out. I want to try this out. So I want to compute the difference of these two paths and see that the answer is a solution to the homogeneous equation. So what's the difference? If I integrated this thing along this path and subtracted this thing integrated along, say, this path. Oh dear, what would I get? It makes it simpler, in fact. So subtracting means go in the path, add, go in the path in the opposite direction. The opposite direction here goes from here. So if I added this contour, then plus this, what do? I go singularity around and then also boom, and then I come back and around this way and this way. And then the straight parts cancel because once I come from the left to the right and then from the right to the left, and they're on the same thing, so I cancel. You know what's left? What is left in the sum? What does that mean? The poles are left. What contour is left? The poles are always there. I can't remove the poles. But what's left of my contour? You mean that? You mean it? Yes, exactly. Just the circle. So here, this isn't canceled. This is from my way there. It's not canceled. And then this is canceled. This isn't canceled. And then I come back. This is added. It wasn't there before. This is what canceled the one before, and this added it. So I have 2 circles. What's the difference between the first and the second? So if I go, what is it? Along this path, first to the right, and then come back this way, then the first arc here will be completely canceled. And then I have a circle right there, only this one. So the difference between path 1 and 2 and 3 is this circle. Between 1 and 4, it's this circle. And so, and that's probably all the combination. We just get circles. And the difference between these two is a circle counterclockwise here and clockwise there. We can do that too. If we go first around in the bottom and then come back at the top. So we have two circles, either way, this way, this way. So let's compute the integral d4d, well, this integral there for these circles. And since we think mathematically, we'll just say positive like this. This is circle C plus, and this is circle C minus, because this is the positive pole, the positive location in this algorithm. So I want to now integrate this thing around these contours. And let's not do the four-dimensional first. Let's look at the dp0 to pi, t plus or minus. We'll call this I plus or minus. And this is now the integrand 1 over just this. P0 no. We take both, I guess. Plus EP P0 minus EP. And then I e to the minus I P0 times P, right? Times x0 minus y0. So let's just look at this, I think. Do I want to look at this? That's the pole for here, and that's not important for this. And that's the pole for here, and that's not important. I'm debating whether I take the other factor. But let's just keep it so that it's easier to relate to this. Now, how do I do this integral? I have to parameterize my circle. So here's the 0, and this is EP. So I say P0 is EP plus, and then have a little circle of radius epsilon e to the pi phi, with phi from 0 to pi. That's if the phi runs here, I'll go in the circle with radius epsilon around this pole. If I want the other pole, I probably have to have a minus in there. The dp0 is this is gone. Then I have I from I epsilon e to the I phi d phi. And we're left with integral. So there's a an I epsilon e to the I phi d phi. Then there's an extra I. Then there's this thing. Let's think about the which pole first. Let's think about which one first. Yeah, let's think about the positive pole first. So I'm inserting the one with the plus. Then I get here just 2 EP plus something with epsilon, but epsilon I will set to 0, so I don't need to bother writing because it's a finite thing. And then it comes minus minus EP. I'm inserting one with the plus. So EP minus EP is nothing, so I have to keep the next term, and the next term is epsilon e to the I phi. That's for the right pole. It's so quiet. You should say no or something.
I have a question. Did we say that we want to integrate it along the real axis?
Yeah, we want to integrate over the real axis. This is what this thing wants, but then we noticed there were poles. And then we had these 4 different ways of doing it, and then I got sidetracked again. Instead of going over the real axis, I wanted to know what happens for the difference. You know, we have these 4 options, and they are probably different. I want to know, are they different?
Aren't we kind of integrating within the imaginary space?
Yes, yes, we are going in the argument was supposed to be real first, right? But then it didn't make any sense, the integral. I mean, we are not happy if it just goes infinity and go home, and then this is just the end of it. So we want to come up with something that replaces this infinity. And one way would be, okay, then we go into the complex plane and get something else. This will give us extra eyes. It will be complex stuff. But since there are eyes everywhere already, I'm not too concerned. So, you know, if you have a divergent real integral and you do something to it to give it a meaning, it often happens that the answer is complex. Yes.
I have one more question. We kind of said that there are like these 4 options to integrate around it. Aren't there like infinite options to integrate around the poles? Like we don't have to do circles, we could also do like
Yes,
squares or something. Or
exactly. You're right.
circles with different
You're
radius.
right. You're right. I have to say that.
So these particularly 4 options.
No, at some point I'll have to. In fact, I was going to say that. There's a theorem that says if you have a closed contour, so you integrate a function f of z along a closed contour in the complex plane, the answer is 0. If that function doesn't have any poles. This is, in physics terms, it's sort of a conservative force. If you have a conservative force and you integrate it along a closed path, the integral is 0. And what you need is the force to be conservative. You have to have sort of the curl is 0. And this function is supposed to satisfy something similar. It's supposed to be analytic, that means it needs to be differentiable in a complex sense, and that imposes other equations that look like the curl. It's called the Cauchy-Riemann differential equation. Like the x derivative of the real part has to be equal to the y derivative of the imaginary part, and these things. So that theorem that this is 0, if that's a function without poles, you can think of it as conservative. Like this is the potential for conservative. So that holds. If I have a function without poles in that region around which I integrate, then I have 0. So if you want a square now, or a rectangle, then the difference between your path along the square and mine along the semicircle is an integral around this box and then back here. So this is the difference between choosing the square and the semicircle. But the integral over a closed curve C is 0 if in the inside that thing doesn't have poles. We figured out the poles are only there, so that contribution is 0. Therefore, of all these infinitely many choices that exist, as you're saying correctly, it's only essential, do you go above or below? The way how you go above or below doesn't matter if you go. This is the same as the semicircle above. really anything, that would be the same as this path. Even this, now it's gonna get a bit crazy. Even this. Above, below, above, around, and coming back. And so now it's, you don't know anymore, but it is netto going above everything. You can do any complicated thing if you stay above. Like now, this is it's a rubber band, and you can pull it, and then it will be above both. So it's the same value as going semicircle, semicircle. Yeah. So we can deform the contour in the complex plane as long as we don't jump fold. And these are the 4 ways to jump fold. This
And what does it mean physically when we say P0 complex?
Yeah. In the end, it shouldn't be like when we put numbers, there's the particle and then there's this energy, then the P0 should be even positive. On the way there to write the formula, it is just an analytic continuation. But we'll use the final result with the P where we plug in a real number.
So choose how often we go around each pole thing.
Oh, yes.
This
You're very good. You're so extremely right. So there's more indeed. We could have this above, extra tour. That would be not included there, and it's a different path. But it is like if you have these as a building blocks, we'll just add a circle on the left twice.
Yeah.
Right. But there's a more here now we're talking, yes.
I know what happened to the epsilon e to the it in the left bracket.
Here,
Yeah.
it's go on. So what it really was is dp plus epsilon e to the I phi plus dp, and then it's ep minus plus epsilon e to the I phi minus dp. Well, while I'm at it, 1 second, minus I, and here is plus or minus dp plus epsilon e to the I phi times x0 minus y0. And now let's make it completely correct. So plus minus, so it goes like here, plus minus plus minus. Now we have it. And now you still not have, yes, now you're happy, right? I inserted everything. Now I can start messing. I have in mind epsilon to 0 at the end. And there are some places where I can do this now. Since here for the upper sign, I have 2 EPs, which is a good finite value. I don't need my epsilon. I can set epsilon to 0, and that's how it disappeared. There was 2 EPs. If I did this here, because they cancel for the upper sign, if I send epsilon to 0 in this term, it would blow up. So I have to keep it. Here I didn't, here I had to keep it. If I'm talking about the lower sign, I can get rid of it here, but I have to remove it. I can't remove it there. And now I'm doing too many cases at once, I guess. Here I don't need it because there's something finite already. So I'm going to throw out. So first of all, because it's confusing, let's stick to 1. The plus integral. And then the plus means it's the upper side. And now we throw this away and we throw this away. And this cancels anyway. Now, there's lots more that cancels. This epsilon cancels this epsilon, that's the magic. This e to the I phi cancels this e to the I phi. This I stays, well, it makes a minus for this one, I guess. Minus 2pi. Then this integral, because nothing depends on phi anymore, this has canceled. And then I set to 0, we have epsilon, so nothing depends on phi, I get 2 pi. of the integral. Done, 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 and then we have e to the minus I dp vector x0 minus y0. And down here, I have still 2 EP. This we cancel? Yeah, this we cancel. So the I plot is minus e to the minus I p vector x0 minus y0 over 2 p. And the I minus the other one would have a, you know, a minus sign down there. It'll be plus 2 p vector p to the I p x0 minus y0. You won't believe it. What is this? Well, let's add the three-dimensional ones. So integral before p 2 pi to the fourth I over p squared minus m squared e to the minus I p x minus y. This thing integrated around c plus is equal to that expression integrated over the three spatial momenta. But this expression integrated over the three spatial momenta has just been erased from the board. Oh, I can't believe it. You remember this thing? That's a minute ago. No, that's exactly this, right? So 2e with this exponent. It's exactly that. So that is minus 2e x minus y. So this thing isn't defined by itself. If we took for fun, just this circle, we'll get our propagation amplitude with a minus sign. If we have a minus, we don't get the minus sign, but we get the other order. But it's one more time. This is here for going plus this, and then we're going minus. It's not what I wanted, right? You were right. We're not supposed to go on a real line. Yes. For fun, I just looked at what happens if I go around the circle. Why? Because going around the circle is the difference between these four proposals. And we said the difference should be a solution to the homogeneous equation. And it is. Because these D's solve the homogeneous equation. So this ambiguity that we get from picking a contour is exactly related to the fact that this differential equation doesn't have a unique solution. Now, well, now I'm coming back to what you wanted, like pick a path and compute it. And so let's pick the path. I think I'm going to pick. Which one do you want to pick? The first one? Shall we start with the first? I think that almost makes sense. So let's start with this. And and I know that we can deform these contours. And I know that the integral around these poles give these two things. And I know, what do I know? What do I know? I guess that's what I know. You see, I want to simplify my life. I don't want to do all the parameterization and all this. Instead of this open contour from here to there, from minus infinity to plus infinity, I want to close it. I want to continue that curve and close it. I want to close it either this way or this way, say, to complete it with this arc. Then I've added things to my integral. And it makes the value different. Unless, for some reason, this path doesn't contribute. So what's my integrand again? The integrand was e to the p squared minus n squared. So p0 minus dp p0 plus dp, like this. And upstairs it's e to the minus I p0 x 2 minus y0 plus I p vector x vector minus y vector. And now if I close this up here, my p0 is imaginary. So up here, p0, imaginary part of p0 is larger than 0. And then we have in the exponent e to the minus I. What is that? P0. You see, this is the crucial thing. Can you get this to 0? Can you make this to 0 somehow? Like add contour that this doesn't get any, that we don't, that our integrand doesn't contribute along the other path. See, if we know that e to the negative goes to 0, if that's just large, right? E to the minus is 0. Perfect. This is what I want. Yes?
But doesn't go to 0 because of the denominator? Because you divide by infinity?
Yeah, but I also have the p0 here. Wait a minute. That helps, yes. The denominator helps too. But this one shouldn't counteract. If the denominator goes to 0 and this one goes up, then the exponential function will survive, will win. So I have to make sure that that doesn't blow up. Can you actually see whether do we need to post the curtain? Yes.
I think if x is bigger than y, if 0 is bigger than y, then the imaginary part of the number is negative or something.
Maybe we can do that, right? So
And
we have so many signs. We have the sign of this, we have the sign of this. So let's say different. So if x0 is larger than y0, big that. So then this thing is positive. And I want the whole thing to be a very negative number, this is I times something, this becomes plus, so the something should be negative. What you just said. So if x0 is larger than y0, and p0, imaginary part of p0 is less than 0, and the actual value of p is infinity. Like we go around this big circle here. Huge p0. It doesn't even need to be because if you don't, but it should be a negative, it should be down here. Then e to the minus I p0, x0 minus y0 is either finite or close to 0, right? So this path doesn't actually contribute in this case. No?
But doesn't additionally the real part of P0 has to be 0?
Which part?
The real part 0?
No, because the real part will just have an extra complex exponential, which is bounded.
But don't we then
It's bounded. It's e to the I stuff. It still does. Right?
isn't it then 0 plus something? Plus
No,
something,
times.
plus something complex?
0 times complex. It's e to the a plus ib.
Yeah.
And then I have e to the a, e to the ib. And this is a hopefully negative, and then we go to 0, and this is times the complex. Aha. So in this case, we can actually add this conjugate down here. So if that's the case, what's the answer then? The in this case, the we're always computing ds. By definition, this thing. It is given by so, and we have decided to go above and above. That's what we decided. And if this condition is satisfied, then we can continue the contour around here. And the integral above, just above is the same as the integral above enclosed. But the integral above enclosed can be deformed into something that just goes around the two poles, or even like this, and this middle piece cancels, so it will be that plus that. And we have just done that. So this integral under this condition is the same as going around this pole plus around this pole. And now we just have to figure out the signs. We want to go around the left one clockwise, so we have to pick this to the other side. It's equal to minus b y x minus b y minus x, this thing. And the other one is also the opposite sign, so it's plus. B x minus y minus b y minus x. That's the answer under this condition. If x0 is less than y0, it's all different. We can't close it here, because if you did, we get a contribution here, and then the value of the integral is changed. But since now the sign here flips in the exponent, we can close it the other way without changing the value. So of this integral, going above with this condition is the same as going above and closing above. But then we have this a region but there's no poles in there, it's zero. So under this condition, it's zero. Oh, I'm so dumb. This was pedagogically amazing. I called this DF because we wanted to compute it. And then we saw this is not even defined. So it isn't really DF, it's nothing. And I'm trying to make sense out of it. And here we found that this integral is this or this, and that's not DF. So I shouldn't call it DF. I shouldn't call it DF. What would be really pedagogically okay would be this integral for I want to have shorthand. But the shorthand wasn't good. So this integral explicitly is zero under this case and this case. And now to be really explicit, I have to write what I mean. Above and above. That's now right. So this is not the F. Above is this in this case, and it's zero in this case. You can even write one formula for both. I could even write a formula for both with the theta function. I could write integral d for b 2 pi to the 4 I d squared n squared e to the minus I b times x minus y is equal to theta x0 minus y0. And then d x minus y minus g y minus x. So that's now both cases. And I have to write it. I have to write pole above. Because without saying that doesn't make it's just not defined. Now, the question to you, can you see what we need here to get theta because this thing is TF. That wasn't, but this is. How do I have to go around these poles to get precisely this? Can you or can you not? So we want to think? Probably better. Yep. Up and below?
So below the unknown is for the one above, so this here is for x greater than y0, and the circle is integrated in the other direction, so the sign should split on the dy minus x.
You want above and below, or above and below?
What? First above and then below.
The funny thing is, I remember the other way around. It's one or the other, right?
Yeah.
Let help us. So we know we want dx minus y. So if the x is front, it must be the right pole. So this must come from the right one.
It's the other way.
And we want the other side, so we don't go this way, we go this way. This will give us dx minus y. And y minus x is the other pole. And the sign is okay. So we do want this way around. And when do we want it? Is that gonna work? We want it here if x is larger than y. So if x is larger than y, we have to close below. So this means we have to be able to close below. So yeah, you know, below. We need to just circle this thing. So in here, it's for the other above. We want to go around here, the closing above. So we have to expand this loop. This loop, pull it more. Right? That's what we want. If we go around the circle, we get this thing, and we want the straight line closed above. So that's what I see. And here we want to go around this one, and we want it straight line closed below. And it even has this border that we want. Yeah, so that's it. It is below, above, closing, below, above, closing. So below, above. Right. So this is our final propagator, df, in fact, has this momentum Fourier representation as I over p squared minus m squared. However, you have to tell us how you want the poles to be handled, and we want them to be handled to go below and above. And that's it. That's your thing. And now you don't like to draw these things all the time under every integral. Like that's already a long hook, and that's just not acceptable from economic point of view. How can we remember? How can we write this without writing this? So instead, we have drawn this because the contour isn't the real axis. It isn't canonical. If it was just the real axis, we wouldn't have to write it. So let's try to turn this into the real axis. So this should be now the same. But then it hits the poles. But instead of making the contour go this way, we can say, hey, step aside. Step aside. So the poles are going to step aside now, rather than us driving there. The pedestrians have to go. Now, what does that mean? Now the pole here is at minus EP, but a little bit above. And this pole is at plus EP, a little bit below. Now we have given the poles in imaginary parts, plus or minus. And I hope that helps. Now, how does the denominator look like with these poles? We had 1 over P0 plus EP, P0 minus EP. So that's what we had. And now we replace this where this is the pole at minus EP. And the one at minus EP is replaced by this. So I have p squared plus EP minus I epsilon. And 0 minus EP plus I epsilon. So that's this one. And it's shifted by I epsilon, but with this extra minus sign. Minus. That function had the poles on the real axis, here and there. This one has the poles off. In fact, the one on the left is a little bit above, the one on the right is a little bit below. It's that. So if we replace in the integrand, replace this integrand by this integrand, we can go straight across and still get the same answer. Because here we go below and then we go above. And now what is this? Multiply it up. P zero squared. And then minus P squared. And then the mixed term with the I epsilon. So we have I epsilon, let's do it slowly. Minus P0 plus BP plus P0 plus BP and then order epsilon squared. So it is P0 squared minus BP squared. And the P0 goes away. And so we have 2 I epsilon BP plus order epsilon squared. Since we're taking epsilon to 0, and we have a linear term already, we really don't need this 2. And if we take epsilon to 0, 2 EP times epsilon goes to 0 as well. And EP is positive, so we are not having a negative radius or so. So this, since this is positive, this combination is just good in epsilon as the other epsilon. So I might as well just drop the 2 EP. So just as good is to have this E0 squared minus EP vector squared plus I epsilon. If you wanted, I should call this epsilon prime, and then next we can get the prime. This epsilon is not this epsilon, but it's as good an epsilon. Yeah. So, but this one, the p squared minus e squared is the same as p squared minus m squared. Here comes the final answer. Oh, let's look at this. This is
Oh,
amazing.
before you.
Yeah.
Want to ask, how, can you please explain again why that is the same integral? Why that phi is df x minus? The one at the bottom right, the equal sign at the bottom, we have exactly that equal. Why is that the same?
That was in the very beginning, the definition, so df.
It's on the left board, you're just going to delete it.
No, you don't see, sorry. Okay. This, the definition is that. This quantifies df. Then we spelled it out with the time ordering and saw, then it's this. Because the one without the d, without the f, it's the same, just no time ordering. And then we got this equal sign. Then we drove the
Okay, it's time order.
differential equation for the d f. Identify this as a Green's function. And then we went to the Fourier space, and then we could solve the equation, and that was the answer. And then we went back with the Fourier transformation, got to this formula. So this was, I said, we have to talk about it before you have minutes to talk forever. So at some point, this was our result. Naive, we thought that's the answer. And then we figured, wait a minute, that is not an answer because that's not defined. This is a pole in the denominator. So we have to actually give this a meaning by saying how to go around those poles. So then I should have deleted the f, because this is some arbitrary thing. And only when the contour is right, then this is the f. And then we worked and worked and worked and worked and found the contour needs to be this. if the contour is below, above, then it is actually df according to what it is defined. Now we got tired of drawing these contours and figured out an alternative way. Instead of going below, above, we shift the poles a little bit. And if we don't use this thing, this is p squared minus m squared. P squared minus m squared is this. If we use this, p squared minus m squared plus I epsilon, and that is also poles, but they are shifted like this, a bit above, a bit below. And now we can write the answer really, if I may, I'll just keep this and add plus I epsilon. And now it is the df. Now it's df. And it's the answer. And here plus I epsilon. These things with the plus I epsilon, they are called pole prescription. Because you prescribe what to do with those poles, you shift them a little off the real axis. And if you do plus I epsilon, this particular one is the pregnant pole prescription. And if you had a different one, like this, above, you wouldn't get df, but you would get this thing. And what is it? This is theta x0 minus y0, and this is the commutator. Well, I don't know if this is necessary, but that would be a different Green's function. Since it is only non-zero if the time of the left field is well, if the x0 is larger than y0, we call this retarded. This is dr, the retarded propagator. What's the time? Oh, no, I'm not over. Remember this Green's function business? If whether g x minus y is delta x minus y, or yeah. And then f of x is integral g x minus y rho y dy. This f solves this equation. So we want this equation. Say this is the source of something. There's someone, harmonic oscillator, and that's the force. And x is time. Okay. X is time. This is the kinetic and potential time acting on the displacement, and this is your force. So what usually happens is you shake it on one side of the string, and then it reacts to it. So I guess if I act at a certain time, I want this to react at a later time. So if this is my solution, usually when you have a forced harmonic oscillator, you look at the particular solutions. You don't care about the homogeneous oscillation on top of it. You want to see what's the reaction to your shaking. So I really look at this particular solution. And if I picked a propagator, like a Green's function solving this with the additional property that G would be such that it's proportional to theta. If that's the case, I call it the retarded one. Why? Because if that's the case, this integral will be cut off, right? It only contributes here when this argument is positive, because this is by assumption theta. So this needs to be positive. if I want to know what happens at 10 o'clock or so, then which wiggles matter? Well, the ones before 10 o'clock, because the integral here, which is from -0 plus infinity, gets cut off when the y reaches the x. Because if the y is of size x, then the g is 0. So this integral is really only until 10 o'clock. Everything before, what you did to it before matters, but not after. And so that's kind of the normal thing, and we call it retarded, because there's like a delay between your wiggling and the reaction, and not the reaction before. The opposite is called advanced Green's function. So then the effect is before you're wiggling. So G advanced is theta y minus x, the opposite order. That is very unphysical from our thinking. Mathematically, it's fine. You can solve it this way or this way. The difference is then you have to add homogeneous to it. You have to solve, if you want to write down what does your oscillator do when you whatever you wiggle between time 1 and 5, and you use the retarded one, then everything is cool. Before 1, nothing happens. Between 1 and 5, you just pick up the part between 1 at the time, and if it's after 5, then you pick the entire wiggling action. So that feels natural. If you did the other way around, the advanced, then the position of your oscillator at yesterday mattered. Is computed from your wigglings between 1 and 5. And how is that? Well, you just add a homogeneous equation on top of it, and then it gives the same function. So I don't know, if you want the physical sensible thing, and not writing the homogeneous solution to the equation, just the particular solution, then you have to pick the right Green's function. You can write out the general solution with the coefficient and match it. But if you have a certain situation in mind, then you can get away with this without the homogeneous solution if you pick the right Green's function. Therefore, you have different ones to pick from. The quantum field theory wants the Feynman propagator because LSZ says we need the time order correlation function, so that's why we want the DF. But there's the others are also around. We don't use them in quantum field theory, the retarded one, but it still is there. It's just different code prescription. Yes.
We had, before we had 4 cases, but only with 2 cases now. And we had 4 cases to go around the poles, and now we introduce this shift, and we only have 2 cases left.
No, you still have all 4, but the really interesting one, the really for us that matters is this one with this plus I epsilon and the df, and it is just to record it. It's the one below above. This is what we really want. The other cases exist still. Above is the retarded one.
Yeah.
Below is the advanced one.
Would be minus
And-
shift then? Would it be minus? I mean, below would be minus the retarded.
Below is not minus. Below has a different theta function because it has nothing for x0 minus y0, but it has something for y0 minus x0. And that's the advanced one. And then you have above below, which is the sort of the anti-version of this. While this is the propagator, this is physically the one that goes from the earlier to the later always. The above below is the one that always goes from the later to the earlier. And we don't care. I found only one person who gives it a name. It's Greiner. In his book, he calls the one above below the Dyson propagator, rather than the Feynman propagator. But then you go and Google Dyson propagator just to cross-check, is that really what people understand it is? And it doesn't seem to be so. You just had to come up with a name, and you can forget about it, because we're doing quantum field theory, and it'll be this one that matters. And the reason why this matters, because there's this time ordering.
And how would the Dyson propagator look at this representation?
Oh, I wasn't on the homework. I wanted you to figure out how the I epsilons, where do the I epsilons need to go for the other one, so that you actually do this computation again. So I can't answer that. You go first.
Yeah, how would I physically understand like different, like if I go around multiple times around the first one, I would like get a scalar with the scalar.
Well, you did get a square here,
Yeah,
and I really don't want that. Right? Every turn will be a power.
yeah.
Am I stupid? Wait a minute. Wait a minute. So why square? It's just you extend it. You get your 2t. It's not so bad. It's not so bad. Mess up with the 2, yeah. I don't have a name for that then, like another propagator, the double propagator maybe. It's not so bad as the square yet. Yes.
Yes, I don't know if I blanked out at some point, but.
My fault, sorry, yeah.
I don't quite get yet where we use any green function stuff. Like,
No.
We didn't yet?
No,
Okay.
we didn't use the
Because I
fact
thought-
that it solves this homogeneous equation with the delta function for anything. We just saw it does and then used it to find the mental space representation. Right, this I is the delta on the right hand side. But then we haven't yet used the Feynman propagator for anything. We have an expression now, we haven't used it for anything. We will, like this Wick theorem, the one that I was going to do today, but we are not going to. So now the next thing will be 5, 5, 5, 5, 5. Many of them. And the answer will be, you have done something like this without the time ordering in the homework, right? There were the D's, the different D's. And with the time, it's so funny, it's the same formula, just with the S. The S, the S, plus. So all these things. And so there will be the DF again in this. So we will use it again. You don't really need that this is a Green's function either. I think when you do class integral quantization, then you need the interpretation as a Green's function makes more important. Yeah, it's just a curiosity. It's just
We just saw that.
we just saw that, yeah.
Maybe we wanted to hold for some. But I don't know which one.
Right. In fact, you could go with root 2 when you define the asymptotic states. You could say, okay, I want to. I have. We have this. In the interacting case, we have not 0, but something really complicated there with 5. If it's lambda pi to the 4th here, then you have minus lambda 3 factorial 5 cubed. This is the equation. And then you could say, oh, let me solve this. And you replace this right hand side by the sum function, and then you have an inhomogeneous equation. With this as the Klein-Gordon operator. And you say, oh, well, it might be probably interesting to have the Ritz function here. This is an alternative approach, which I thought is longer and didn't show you. Okay. Well, so this will be next, to split this up, the endpoint function. And then the step after this will be go back to interaction theory. What do we have to change if this is the real vacuum and these are the interacting fields? And then we finally compute the scattering amplitude for a real closet. Okay, thank you for today.